So we've been doing planar kinetics problems, and in Module 11, we did examples of translation of a rigid body and rotation of a rigid body. In Module 12, we're not going to cover any new material, but we are going to do some more complicated examples. And so here's the first example. This is general planar motion. So here we have a slender rod, and it is fixed to a roller at point A. It's free to rotate, and roller A is confined to this frictionless slot, so it can move side to side. And at time t0, our rod is at a position such that theta is 0. So our rod is horizontal. And at time t0, that rod is released and it starts to do whatever the forces are going to cause it to do. So we're asked to find the angular acceleration of the rod and the acceleration of the rod's mass center just after it's let go. All right, so the first thing that we're going to do, just because we're going to need the mass moment of inertia, you can wait if you're working a problem, you can wait until you know that you need it. In this case, I know we're going to need it, so I'm just going to go ahead and find the mass moment of inertia. Now, we need to decide what point we're going to work with. So we could absolutely choose the center of mass, right, point G. We could work with point G, and that's fine. In this case, I'm going to work with point A. And so I'm going to find the mass moment of inertia about point A. And so over here on the right, we have a picture, and you can find the mass moment of inertia pictures in the back of the book or on the formula sheet. You just have to find the shape that corresponds to the shape that you're working with. And so here we have the slender rod, and we've got the formulas for the mass moment of inertia about the various axes. Now, our point A is rotating about an axis that kind of goes into and out of the screen. And the corresponding axis on our picture, it would be either x primed or y primed. And x primed or y primed have the same mass moment of inertia formula. So that's right there. So that's our formula. So I'm just going to write this. So it's going to be 1/3 ml squared. And I can just fill in values. So the mass of our slender rod is 12 kilograms. And its length is 0.6 meters. And that's going to be squared. And so if you do that calculation, you should find that the mass moment of inertia of our object about point A is 1.44 kilogram meters squared. All right, so that's a good start. The next thing we're going to do, as we frequently do with kinetics problems, we're going to draw a free body diagram. And so this is, and actually we're going to do a kinetic diagram too. So this is going to be my free body diagram. And we always start with an inertial reference frame. And so in this case, so I could draw, the traditional X and Y directions. In this case, let's just think about this. We've got the mass center G that we need to work with. And it's going to be moving kind of, in the vertical direction. It might move in this horizontal direction as well. So I want something that aligns with this negative vertical direction. And so I'm just going to make that my E1 direction. And as I said, you can do this however you want, but this is going to be my E1 direction. And then it's going to be rotating clockwise initially, right? And so I want a unit vector that's going to be positive in the clockwise direction, right? So I want a unit vector that's going to be kind of like that. I'm going to make this my E3 unit vector. And so now I need an E2 unit vector such that E1 cross E2 is going to be E3. And so that means that my E2 direction needs to look like this. Yeah, so now E1 cross E2 equals E3. and my E3 is positive in the clockwise direction, which is how I anticipate my my rod will be rotating initially. Okay? Okay, so there's my initial reference frame. I'm not going to add any other reference frames in this case. You could, especially because you're probably anticipating curvilinear motion, and when we have curvilinear motion, we often add either polar coordinates or normal tangential components. You could do that in this case. You really don't need to. So I'm just going to work with this E1, E2, E3 reference frame. Okay, and then I'm gonna add my forces and my moments. And so we know we've got a force, the force of gravity, of course, we always have that. So there's the weight. And we've got some other force here, right? We've got this force at A. So this is, I'm going to call this the normal force. So this is just the force that the slot is exerting on point A. All right, and I think that's all we have. All right, and I'm going to go ahead and do my kinetic diagram now. So let's see, so I've got an acceleration. Again, I'm working with the mass center. So here I've got MAG1, and I'm going to have MAG2 as well. So MAG2, I'm going to draw it kind of just above the rod so it's easier to see. So here's my MAG in the E2 direction. And then I'm going to have a rotation, and so I want to represent my alpha, my angular acceleration, and it's going to be in this clockwise direction as well, right? So this is going to be IA, because I'm working with point A, alpha. Okay, and I should have said this is my kinetic diagram down here. All right, good. All right, so next step, equations of motion. So let's do equation of motion in the E1 direction. So EOM, E1. So this is going to be sigma F1 equals MAG1. And whenever we write equations of motion, we're always working with the mass center. When we do a rotational equation of motion, we can choose our point. But at least for the translational equations of motion, we always use the mass center. And so, I'm going to expand my forces. So we've got in the E1 direction, we've got the weight force, which is acting in the positive E1 direction. The normal force is acting in the negative E1 direction, and that's going to equal MAG1. We know the weight force, we don't know the normal force, and we don't know AG1. So I think that's it. I don't think that there's much that we can do with this. And that's okay. Like sometimes you write an equation of motion and it doesn't help. Maybe it will help later. I'll write it over here to the side. It may come in handy, it may not. That's okay. MAG1. All right. So let's see if we can fit in the equation of motion in the E2 direction. EOM E2. This is going to be sigma F in the E2 direction equals MAG2. Do we have any forces acting in the E2 direction? I don't think we do. So that's just going to be 0, right? So 0 equals MAG2. And so the mass is not 0. So that means AG2 is in fact 0. Okay, so that's an important finding. I'm going to write it over here on the right. MAG2 is 0. Okay, great. And now I'm going to make a little bit more room. And I'm going to write the rotational equation of motion now. So rotational equation of motion. And let's see. So I'm going to use this equation. So I'm working with point A. Point A is fixed in and rotating with my rigid body. So that's a point Q, right? So Q is always fixed in and rotating with a rigid body. So I'm going to rewrite this equation, and I'm going to change all of the Q's to A's, right? So here's my sigma, the moments due to forces about point A, plus my pure moments, and that's going to be IA, the mass moment of inertia about point A, alpha of the rigid body as seen from E, plus the mass times the mass center with respect to A cross the acceleration of A as seen from E. All right, so now can we get rid of anything? We don't have any pure moments, so that's going to be 0. We definitely will have an angular acceleration. That's actually what we're looking for here. Mass is not 0, position vector is not 0. We don't know acceleration of A as seen from E, so that's all we can get rid of. And so I'm going to expand the this moment term. So the moments due to forces are always R cross A, right? So I'm just going to write this a little bit more precisely. So more precisely, this is going to be the position of. So I'm working with the weight force only, right? Because this normal force acts through point A, so I only need to worry about the moment exerted by the weight force. So we need this position vector from point A to point G, right? So this is going to be the position of G as seen from A. So this is the position of G as seen from A, cross the weight force, and that's it. That's it for the moment, the weight. That's it for the forces that create moments about point A. And then I've got I sub A alpha. Oh, and I'll just go ahead and write this. I'll add some more precise terminology in the next step. Plus, and this is going to be mRg with respect to A again, cross the acceleration. Okay. All right. So let's see, what else can we write here? So the position of G as seen from A is going to be, this is going to be negative half of the length of that rod. So I just want to use variables as long as I can. So I'm going to call the length of the rod L. So the position of G as seen from A is going to be half of the length of that rod, right? And that's going to be in the negative E2 direction, right? And then crossed with the weight force is going to be mg, and that is acting in the positive E1 direction, right? Okay, and then that equals IA, and I'm not going to fill in that value yet. I know it, but I'm not going to fill it in yet. Alpha of the rigid body as seen from E, I'm just going to call this alpha, and I know it's acting in this E3 direction. I strongly suspect it's acting in the positive E3 direction, but I'm not going to assume that yet, but I'm going to just write it as positive, and the equation should tell me if it's positive or negative or not. Plus the mass times, again, the position of G with respect to A is negative L over 2, E2, cross. Now, this acceleration of A with respect to E term, here's what I'm going to do with that. I'm going to expand it. So I'm going to write it as the acceleration of A in the E1 direction, E1, plus the acceleration of A in the E2 direction, E2. And I'm doing this because that's going to make it much easier for me to take that cross product. Okay, so I'm just going to expand that. And I just want to make sure that I point out, I'm keeping the acceleration of A terms, like I've got acceleration of A here, I've got acceleration of G here. In problems like this, they're not going to be the same. And so I want to make sure that we keep them separate and we realize that they are separate accelerations. Okay, so we absolutely need the subscripts with the points that we're working with. All right. So in the next step, I'm going to take those cross products, and so negative E2 cross E1 is going to give me a positive E3. So this is going to be mgl over 2 in the positive E3 direction. That's the left side. And then the right side is going to be IA alpha E3. That's going to stay the same. Plus, and I'm going to have an ml over 2. Okay, and then I need to take a cross product. So E2 cross E2 is always going to be 0. That doesn't mean that the acceleration of A in the E2 direction is going to be 0. It just means that E2 cross E2 is 0. So that's I'm going to not worry about that, but I am going to worry about this negative E2 cross E1. So negative E2 cross E1 is going to be a positive E3. So this is going to be positive MLA in the E1 direction over 2 in the E3 direction. The cross product is going to be in the E3 direction. Let's see, do I have everything in there? I think I do. It's a lot to keep track of. All right, and now I have two unknowns, but maybe I can get rid of something else. So what about this acceleration of point A in the E1 direction? Can we say anything about that? So let's look at our picture. So A is confined to move in the horizontal direction, right? So this is the E2 direction. But point A cannot move in this E1 direction, right? It's confined to move horizontally. So we can say that this acceleration of A in the E1 direction is actually 0. And so now, so we could cancel those E3s. We just need to kind of remember that everything here is going to be acting in the E3 direction. But now we should be able to solve for alpha. So alpha is mgl over 2ia. And now we're going to plug in values. So we've got 12 kilograms times 9.81 meters per second squared times L is 0.6 meters divided by 2 times 1.44 kilogram meters squared. And if you do that calculation, you should find that alpha is 24.5 radians per second squared. Now, it's always a good idea to go back and just check the units, because if the units aren't right, you need to fix something. So here's kilograms is going to cancel. We've got 2 meters in the numerator. We've got 2 meters in the denominator. So that's going to give us radians per second squared. So that looks good. I'm going to write my alpha value over here, 24.5 radians per second squared. And of course, if we were going to write this as a vector, this would be alpha of the rigid body as seen from E. And of course, this is acting in the positive E3 direction. All right, so that's good. That's half of what we needed, right? So now we just need to find the acceleration of the rod's mass center. So let me delete this to make some more room again. Yeah, like this. And all right, so now we need something else to help us find acceleration, right? Let's try kinematics. So here we have the rigid body equations for general planar motion, and here's one specifically for acceleration. So let's try that. So we're going to use kinematics now. Oops, kinematics. And I am going to translate the acceleration equation. So I don't want the acceleration of b with respect to e. I want the acceleration of g with respect to e. So let me just translate that. So this is going to be the acceleration of g as seen from e. And I'm viewing that the mass center g as kind of rotating around point A. Now, you could do it the other way, and I'll talk about that in a second. So here's the acceleration of A as seen from E plus alpha cross the position of G as seen from A minus omega squared times the position of G as seen from A. So if you chose to view this as point A rotating around point G, you would just translate this, as A as seen from E equals acceleration of G as seen from E, and then alpha would be the same, omega would be the same, but the position vectors would be the opposite. So the sign on those position vectors would be the opposite. It will work either way. I'm just going to continue to view this as the mass center is rotating around point A. All right, so what else can we do here? So let's see what we can fill in. And I'm going to do something else. So remember before I expanded that acceleration of A as seen from E, I'm going to do the same thing here. So I'm going to call this the acceleration of G in the E1 direction, E1 plus the acceleration in the E2 direction times E2. And I'm going to do the same thing for acceleration, A1, E1 plus the acceleration of A2, E2 plus alpha. We know alpha. I'm just going to call it alpha E3. I'll plug that in a minute. Cross the position of G as seen from A, and that's going to be negative L over 2 in the E2 direction, I think. Let's just check that. Does that look right? Negative L over 2 E2. Okay, good. And now, what about omega? So omega, so remember, we're looking at this problem just after it's released. And so initially, the angular acceleration may not be 0, but the initial rotational speed is going to be 0. So we can just say that is 0. All right. Now. Okay, what can we do now? So we know that the acceleration of G in the E2 direction is 0, so we can get rid of that. We know that is 0. Okay, so that's pretty good. And now I want to do something else. So since I know that the acceleration of the mass center in the E2 direction is 0, I can now just work with this E1 direction, right? And I can say that AG in the E1 direction is the acceleration of A in the E1 direction plus alpha E3 cross negative L over 2 E2. And we already said that the acceleration of point A in the E1 direction has to be 0, right? Because it's being constrained to move horizontally by that slot. So the acceleration of G in the E1 direction has to be alpha. I wrote EX and I did not mean to write EX. I meant to write alpha E3. Sorry about that. So now we have E3 cross negative E2. That's going to give us a positive E1. So this is going to be alpha L over 2 in the E1 direction, and I think now I can plug in values. So 24.5 radians per second squared times 0.6 meters divided by 2. So that should give us the acceleration of g in the E1 direction is, if you do that computation, should give us 7.36 meters per second squared, and I'm just going to write this as a vector. So the acceleration of g as seen from E is just 7.36 meters per second squared in the E1 direction. And that's all there is to it.